Hey everyone! Today I'm going to show you how to do question 2 of this week's homework, which is question 63 on page 547 of the written edition of the textbook. In 2003, an earthquake in Japan generated a 1.1 Hertz wave that traveled outward at 7.0 kilometers per second. 200 kilometers to the west, seismic instruments recorded a maximum acceleration of 0.25 g along the east-west axis. Now, before we get into answering the subparts of the question, let's write down what we know. So we know that the waves are 1.1 hertz. Now, what has units of hertz? Well, frequency does. So our frequency is 1.1 hertz. So let's write that down. We are also told that the waves are traveling with a speed of 7 kilometers per second, so we'll make note of that. In addition, we're told that 200 kilometers to the west, we have instruments that are able to detect the waves. So that 200 kilometers, that's going to be the distance between where the earthquake started and where the instruments are. So I'm going to denote it with a delta x. And we have one more piece of information, but that's not going to come into play until later in the question. So in the interest of keeping the board a little bit cleaner, we're going to hold off on that. So part A of the question asks us, how much time elapsed between the earthquake and the first detection of the waves? So in part A, we want to find a time. So if we look at the information that we have, we know that there are 200 kilometers between where our earthquake started and where it's measured. We also know the speed at which it's traveling, and it's a constant speed. So this means we can use our old friend, v is equal to delta x over delta t. So since we're looking for time, we're just going to go ahead, multiply both sides by time, and divide by velocity. And we'll get that delta t is equal to delta x over v. From here, it's a matter of plugging in our variables. Now, if you look here, we have units of kilometers here and here. Now, normally we convert to meters to get things in the appropriate base units. However, the kilometers are going to end up canceling out, so in this particular instance, it doesn't actually matter whether you convert to meters or leave it in kilometers. I'm going to go ahead and convert to meters because it's good practice, but I saw a lot of people solve leaving it in terms of kilometers, and that's okay too in this case. So if we go ahead and plug our values in, this is going to become 2 times 10 to the 5th meters. And then this one's going to be 7 times 10 to the 3rd meters per second. So now if we plug this into our calculator, we end up getting that delta t is about 28.57 seconds. Because our units of meters are going to cancel here and here. We have 1 over seconds in the denominator, so that's going to flip up to the numerator. So that's how we get our units of seconds. Now, if we look at how many sig figs we have in the different parts of this problem, we have only 2 here, so we only want 2 in for our final answer. So delta t is going to be equal to about 29 seconds. And that's the answer for part A of the problem. Now, part B of the question asks us, was this a transverse or a longitudinal wave? To figure this out, we're going to turn to page 520 of the written textbook. It should be about that same page in the ebook, but it might be off by a page or two. And we're just going to look at what the definition of these two types are of. So for mechanical waves, a transverse wave is a wave which the particles in the medium move perpendicular to the direction in which the wave travels. In a longitudinal wave, the particles in the medium move parallel to the direction in which the wave travels. So if we think about what's happening here conceptually, we have the origin of our earthquake, which I'm going to draw as a little dot, and we have waves that are traveling outward, so we could draw them as concentric circles. So kind of a top-down perspective. If we had an aerial view, it would look like this. Now if you think about what's happening with the Earth, it's going to be kind of getting compressed and stretched in the direction of the motion. So the motion is going to be radially outward. So we have a little velocity vector going this way for this point, and a little velocity vector going this way for this point. So a little velocity vector arrows kind of going outward from the circle at all sides. And so if we think about what's happening here, the particles, there are going to be points of compression happening in the direction of motion. So we're going to end up having longitudinal waves. So part C asks us about the wavelength. Now if we think back to the different variables we had on the board earlier, we know our frequency, 1.1 hertz. We know our wave speed is 7 kilometers per second. And recall also that we learned that the speed of our wave is equal to our wavelength times our frequency. We want to know wavelength, we know V and we know F, so this is going to be a good equation to use. So I'm going to go ahead and solve this out for lambda by dividing both sides by F. Now we'll see that lambda is just equal to V over F. And now it's a matter of plugging in our variables. I'm going to go ahead and convert our velocity to meters per second. Some people solve this in units of kilometers, and that's fine, but I'm just going to use meters. So this is going to be the same thing as 7 times 10 to the third meters per second. And then our frequency is 1.1 hertz. And remember that a hertz is just an inverse second. So this is the same thing as 1 over a second. So the 1 over seconds are going to end up canceling each other out, and we're going to be left with units of meters. So let's go ahead and plug this into our calculator. And we will get that our wavelength is about 6,363 meters. Now again, let's think about our sig figs. We have only 2 here. So we're going to say lambda is equal to 6.4 times 10 to the third meters. So the final part of this question is, in my personal opinion, the trickiest. It asks, what was the maximum horizontal displacement of the ground as the wave passed? Now, to do this, we're going to need to take into account that last bit of piece of information that we didn't put on the board. So the last sentence of the problem says, 200 kilometers to the west, seismic instruments recorded a maximum acceleration of 0.25 g along the east-west axis. So let's just know what that means. So we said maximum acceleration, so that's a max, is equal to 0.25 g, where g is our acceleration due to gravity. So we know generally for our waves, our acceleration is given by the equation. Our acceleration is a function of time is equal to 2 pi times the frequency, quantity squared, times the amplitude, and then times cosine of 2 pi ft, and we have a little negative sign out front. So that's our general equation. Now, we talked briefly about A max last semester when we were doing simple harmonic motion, but you may not have seen it since then. So the idea is that we have to think about what the maximum value of this function would be. Now, this right here is a constant. This is a constant. Cosine is the only thing that varies. So the maximum value that cosine takes on is going to be 1. So we can get rid of the cosine piece and the negative sign because we only want the maximum value, and rewrite this as A is equal to, or I should say A max, is equal to 2 pi f quantity squared times A, and then we're just going to do times 1 because that's what we're replacing the cosine bit with, but the 1 is not going to make a difference here. So A max is ultimately 2 pi f quantity squared times A. So now if we think about what the question is asking for, it's asking for our maximum horizontal displacement. That definitionally is our amplitude here, so we want to solve out for A. So I'm just going to go ahead and divide both sides by the 2 pi f squared, and we're going to get that our amplitude A is equal to A max divided by 2 pi f quantity squared. From here, it's just a matter of plugging in our variables. So A max is 0.25 g, so it's going to be 0.25 times 9.8 meters per second squared. And we're going to go through and divide this by 2 pi, and our frequency is 1.1 hertz. That whole quantity squared. So the last thing you have to do is plug this into our calculator, and we get this is equal to about 0.05129 meters. Our units are going to be meters because we have seconds squared in the denominator here, and then hertz, remember that's the same thing as 1 over seconds. So if we square 1 over seconds, that would be 1 over seconds squared. So the seconds squared in both cases are going to cancel out in the denominators of those two terms, and we'll be left with the units of meters. Now if we look at our sig figs, you've got only 2 everywhere basically, so as our final answer, we're going to say A is equal to 0.051 meters. And that's question 2. If you have further questions on question 2, feel free to ask them during recitation. If you have questions on question 1 and you're one of my students, we did cover that at the beginning of last week's recitation. So if you watch the first few minutes of last week's recitation, you should see what a diagram of a wave looks like. Have a great day.